There are some contexts in probability in which we have a joint probability distribution, and recall that a distribution just as a way of laying out or displaying all 100% of the outcomes. And so maybe we have a joint probability distribution, so we can see how two random variables are jointly distributed across the probability space, and maybe what we want to do is come up with a marginal distribution. In other words, we just want to know the distribution of probabilities for just one of the two random variables. Or similarly, maybe we have two individual marginal distributions, so distributions for each of two separate variables, and we want to find a distribution that shows the probabilities jointly like we have displayed in this table. So let's give this some context. Let's say that X is the number of heads we get in two coin tosses, assuming a fair coin, two-sided, and Y is our status of winning a game. Okay, so we'll just denote 0 if we lose, 1 if we win. And the joint probability is as shown here. Now, what we can see is that the probability, for example, of tossing a coin twice and getting 0 heads and winning this game, this separate game, having those two outcomes, so we toss a coin twice and we get 0 heads, and simultaneously we win some game, there's a 2/20th chance, or 0.1 probability that both of those things happen. But maybe what I want to know is, here I have the probability of X being a value and Y being another value, but maybe what I want is I just want to know what is the probability that X takes on a certain value regardless of what Y does. So what I want to build here is I want to build the probability that X is equal to some particular value without worrying about the value of Y. Well, the intuitive way of approaching this is, well, when X is 0, the probability depends on whether Y is 0 or Y is 1. Now, for X to be 0 when Y is 0, there's a 3/20th chance of that. But for X to be 0 when Y is 1, there's a 2/20th chance in that. So overall, the percentage of all the times, okay, notice that this is going to add to 100%. And just to convert these fractions, this would be 6/20ths, and this would be 4/20ths, just so that we have those probabilities there. And if you add 3 plus 2, that's 5, 11, 15. 15 plus 5 more is 20. 20/20ths, that's 100%. So I'm going to put that down at the bottom. That's the grand total of all of these here probabilities. And like I said, we want to know what's the probability that X takes on a certain value. Well, the percentage of all that 100% that X takes on the value 0 is 5/20ths. 5/20ths. Now, I'm not going to reduce this just because I want to illustrate a point here, but there's a 5/20th chance that X is equal to 0. 3 of those happen when Y is 0, and 2 of those happen when Y is 1. Similarly, the percentage of times where X is 1 would be 10/20ths of the time. And here, the probability, percentage of time that, or fraction of time that X is equal to 2 would be 5/20ths of the time. And notice once again that if you add 5 plus 10 plus 5, you get 100%. Because in essence, we're still adding all 6 of these values. We just collapse them down into 3 values. And this is what we call the probability, the marginal probability distribution of X, of the random variable X. Now, we could do the same thing for Y. What if we just wanted to know how the values, what percentage of time Y takes on its value? So in other words, what percentage of the time do you actually lose the game? Well, in total, that's going to be 3 plus 6 plus 3. That's 12/20ths of all of the 6 outcomes where you lose the game. And the percentage of all the times, or fraction of all the times that we win the game, would be 2 plus 4 plus 2, 8/20ths of the time. And once again, notice that that gives a sum of 12/20ths. So all we're doing here is we're just marginalizing, we're focusing on a specific random variable, and we want to look at it without regard for the other variable. And so what we have down here is we have the marginal probability distribution of the random variable y. And so notice that what we really did is we just summed, to get the probability distribution of x, is we just summed across the values of y. To get the probability distribution of y, notice that we just summed across the values of x. Okay, so again, just to kind of delineate how these are done, we're just summing over the other variable to eliminate it from the picture. And also, by the way, this is really what we have in this table is a point mass function, or PMF. Usually call it a PDF, probability distribution function, if it's a continuous random variable, but both of these are discrete. And so you could actually visualize these as 6 ordered triplets in 3 dimensions. You know, here you have your x-axis, and x could be 0, 1, or 2, and you can kind of see the height of those points displaying that distribution function. Okay, so to summarize, for a discrete joint probability distribution, the marginal distributions of x and y respectively are given by, so if we want to get the probability that x equals x, we sum over all of the y values for our overall, this is our joint probability mass function, and what that mathematically means is we just summed across, and that's all we mean here. And the function that we had displayed in this table is the joint mass function. It's the probability that x equals x and the random variable y equals little y. That's what we started off with. And then when we added across the columns to get one single row value, then we eliminated the variable y and came up with the joint distribution of x. Similarly, to get the probability distribution for just y, we would sum across all of the x's, which we did down the rows. For each column, that's what we did here. Now, one of the things I want you to notice here is that the value in this probability distribution is, now that I can look at and maybe perhaps just be interested in the random variable corresponding to the number of heads that we get in 2 coin tosses. And we've learned previously that you could get 0, 1, or 2 heads when you toss a coin twice. In fact, if you convert these into their respective proportions or decimals, you would get 0.25, 0.5, and 0.25. These are legitimate probabilities here. And furthermore, if we want to just know what's the probability that you win the game, which is a very valid question, well, there's a 60% chance that you lose and a 40% chance that you win. And so this is just a great way to be able to look at one random variable at a time while ignoring completely the value of the other random variable. The situation of discrete probabilities, I think, really illustrates the point for continuous random variables, because with continuous random variables, we're just dealing with functions that don't actually output the probabilities, because keep in mind that when you're dealing with a continuous random variable, there are infinitely many values in an interval, because we're talking real numbers instead of just x being 0, 1, or 2. In the realm of continuous random variables, x can be any number, say, between 0 and 2. And so the likelihood that it's exactly 0 is unheard of, right? So here's a situation where our 2 random variables are actually continuous, and we'll just say that x and y are the amounts of time in minutes that a bus is late at one bus stop, and y will be at some independent other bus stop. And we're going to say that these are uniformly distributed, meaning that the first bus is going to arrive anywhere between 0 and 10 minutes late. There's an equal likelihood. It's not more likely to show up 10 minutes late than it is 0 minutes late. And for bus 2, that bus 100% of the time will show up somewhere between 0 and 5 minutes late. Now, if that's the case, we could actually, we'll see how this is built, but this is not a made-up function based on these. This is actually the exact function, and the output is 1/50th. So does that mean that each output has a 1/50th chance of happening? Not quite, right? Because to say that bus 1 is 10 minutes late and bus 2 is 0 minutes late is not 1/50th chance, because it could arrive any time between 0 and 10 minutes late, even say 5.1296345 and so on minutes late. And so the probability of any exact value within that interval has a 0% chance. And that's why we have a continuous surface now, analogous to this probability mass function. Now we just have this density function. And the density outputs of a numerical value so that the area under here is 1. So if you took the area from 0 to 5 on y and 0 to 10 on x, if you took the area under this region right here, this whole area, or sorry, I shouldn't say area, but I should say volume, the volume underneath this probability distribution function is 1, right? It has a volume of 1 because that's 100% of what could possibly happen in our situation. Now, we could also figure out the probability that say that y is, say, between maybe 1 and 3, and x is between 5 and 6. And so what we would be looking for is just the volume under that surface inside of this tiny little rectangle, right? Which we again sort of just think about the volume of this little prism here. That would be the probability that say x, what do we say? X is between 5 and 6, and y is between 1 and 3. That would be that volume. So it would be a subset of it. But let's just say that what I wanted was just the marginal PDF of x. Well, I want f of x, and I want to ignore the value of y. So think back to what we did over here. If we wanted to ignore the value of y, and we just wanted the probability of x, regardless of the value of y, we summed across the values of y. So how do we do that for a continuous function? Well, it can't be a summation anymore because there are infinitely many values of y. So what we do is we integrate, which is just a way of summing continuously across all of the y values. And so because y could be between 0 and 5 of our joint distribution, so basically what this says is, what is the probability distribution function of x across all the values of y summed together? And you can do the math on this. Get 1/50th x evaluated from x equals 0 to x equals 50. And we know that that's not 50, excuse me, 10, from x equals 0 to x equals 10. And not x. We want to do the value of y, my mistake. Let's try that again. We want to integrate across y, and so that means y will go from 0 to 5. We want to sum out across all of the values of y, so basically eliminate this dimension entirely, and so we will get 5/50ths minus 0/50ths, which will give us 1/10. And so that means that the probability distribution for x is just 1/10. And that's interesting because we had a similar problem in a previous video where we basically said the bus times, it arrives somewhere between one time and another time, but it's a 10-minute interval. And so on a 10-minute uniform interval, in order for this area to be 1, right, because the bus is going to arrive somewhere between 0 and 10 minutes, for this area to be 1, that means width times height has to equal 1, and if 10 times x has to equal 1, then that has to be a height of 1/10. Sorry, f of x times f of x. And so that would be the probability distribution function just for x. And now I could answer questions just related to bus 1 without respect for bus 2. Now for bus 2, if we wanted to analyze it separately, we would just have to integrate out across all of the x's. So we do go dx. It would give us a similar integral, just now summing across the values of x. And we would get 10/50ths minus 0/50ths, which is 1/5. And once again, notice that now we can say that the probability distribution function for y is 1/5. And all that means is that if we look at y versus its mass function, we know that the bus is going to arrive somewhere between 0 and 5 minutes late. Again, this area still has to be 1. So we're ignoring what happened to the first bus, just focusing on the second bus. We know 100% of the time it's going to arrive between 0 and 5 minutes late. And for that rectangle to have an area of 1, it would have to have a height of 1/5. So did we have to integrate? Not really, just because these functions were simple enough. But that's the whole point that I'm trying to illustrate here, just the intuition of how working with continuous random variables is very similar to discrete. Now, let's say that what we just discovered here is for a continuous joint probability distribution, if what you want is the marginal distributions of x and y, you just have to integrate out the variable that you don't want. So integrate across all the values of y, we'll get f of x. Integrate f of xy across all the values of x, you'll get f of y. So that's how to take a joint distribution and make it into a marginal. How would you go from marginals to joints? Well, given a discrete or continuous pair of independent distribution functions, if they're not independent, things get more complicated. But if they're independent distributions, like two independent bus time late arrivals, or two discrete events like tossing a coin twice and winning some game that are unrelated to one another, then to get the joint distribution, you have to just multiply them together. That's pretty much as simple as it gets. So if you notice in our case of the 1/10 times 1/5, you get 1/50th, not surprisingly. Here, if you take 5/20ths times 12/20ths, you'll get 3/20ths once it's simplified, because these events are independent. But if they're not, again, things get a little bit more complicated. We're not going to address that here. So to build joint distributions for marginals, if they're independent, you can just multiply their probability mass functions or probability distribution functions together.